Right triangle trigonometry and SOHCAHTOA. A lot of students I come across have a hard time with trigonometry and just generally dislike it, and I think it's because they just try to get through it and go through the motions. So hopefully you've heard of SOHCAHTOA before and generally know how to use it, but before I review SOHCAHTOA, what I want to do is review functions for a quick second because sine, cosine, and tangent, which are the foundation of SOHCAHTOA, are themselves functions. So real quick down here, let's think about the function x squared. So what I'm going to do is say, well, let's let f of x equal x squared. So this function notation f of x, we use it for many different functions. We say, well, let f of x be x squared. And then the next problem we say, well, let f of x now be x plus 1. And we continually reuse this generic function notation when it comes to different variations of polynomials or things that maybe aren't as interesting, let's say. Well, what I could do if I really wanted to, though, is I could come up with a special name or a special function title for x squared, this squaring function. So, if I go ahead and plug in 3 to what I've just called f of x, then what do? Is I take 3 and I square it. So 3 squared is 9. But let's say I wanted to call x squared something else. Let's say I wanted to call it blue. So I'm going to call blue of x squared. But instead of labeling it every time, you're just supposed to know that blue of x means square anything. So let's say let's do blue of 2. Well, you're supposed to know that blue means square it. So blue of 2 is 2 squared, and 2 squared is 4. So we'll go ahead and take blue of negative 4. So again, it's recognizing what does blue stand for. Well, we just made it up. We gave x squared a name. We called it the blue function. So anytime you take blue of a number, you square it. So negative 4 squared is positive 16. We've just taken blue of negative 4. It's as simple as that. We can make up a name for any function that we want. Well, sine, cosine, and tangent are themselves functions, and they're important because they compare ratios of right triangles. So now let's take a look at each of the trig functions involved in SOHCAHTOA. So the sine function, sine, the SOH part of SOHCAHTOA, means that when you substitute in something into the sine function, what it means is we're going to consider the ratio of the opposite side to the hypotenuse of the right triangle. So that's something that we substitute into the sine function or any trig function. What goes in here is an angle. So notice B in this case, here's B here, it represents this angle. And this angle can be given in either degrees or in radians. Now, for our purposes in calculus, we primarily use radians. So imagine we substitute in some angle here. So this angle B is in radians. And the sine function is this machine that tells us, well, whenever I have some angle here, and I'm trying to take the sine function of that angle, I look at the opposite side of the angle, and whatever length that is, that goes on top of the ratio. And then I look at the hypotenuse, and whatever that length is, I put it on the bottom of the ratio. So the sine function says that whenever I have some angle plugged into sine, I consider its opposite side and its hypotenuse and the ratio between the two. The cosine function, so we're still talking about this angle B in degrees or radians, says, well, this time you're considering a different ratio, the one that looks at the adjacent side and the hypotenuse to the angle that you're talking about. And then finally, the tangent function of the angle is considering the opposite side to the adjacent side. So the sine, cosine, and tangent function, so what happens is you put in angles, so what goes in here is some angle measure, and then what comes out is a ratio of lengths. It's the ratio of the sides of the right triangle, so either a combination of the opposite, adjacent, or hypotenuse of the sides of the right triangle. Alright, so now let's try to use SOHCAHTOA in a quick problem. So what we want to do is find sine of theta, cosine of theta, and tangent of theta in this right triangle situation. So here's my angle theta. Now it's not a specific number in degrees or radians, it's just theta is going to be a variable that stands for a number in degree or radians. So what I want to do is I want to find sine, cosine, and tangent of this angle here. So let's start by thinking about sine of the angle theta. So sine of theta is going to equal, so what went on top of this ratio was the side length opposite. So I'll write up here in the corner in case you forgot, SOHCAHTOA. So sine corresponds to the opposite side of the angle. So opposite theta here is going to be 3. And what goes on the bottom is hypotenuse, but the hypotenuse here is missing. So another formula that I'm hoping is a quick review that you're going to need to know for the class is the Pythagorean theorem. So to find the third side of any right triangle, if you have two of the other side lengths, we're going to use a squared plus b squared equals c squared, where c is the hypotenuse. So here in this example, we'll go ahead and say a is 3 and b is 4, so we're searching for c. So what we have is we have 3 squared plus 4 squared equals c squared. 3 squared is 9, 4 squared is 16. So 25 is going to have to equal c squared. So if I'm solving for c, I would take the square root of both sides, so the square root of 25 and the square root of c squared. But what would come out when I take the square root of a square is I'd end up with plus or minus. So plus or minus 5 equals c. However, c is this length, and it doesn't make sense for a length to be negative, so I can just go ahead and ignore the negative that would come out. So positive 5 is the length of the hypotenuse, and that's what's going on the bottom of the ratio or the fraction here. So now if I want to do cosine of the angle theta is going to be the adjacent side. So here's theta. I don't want an opposite side. I want the side right next to it that's not the hypotenuse, so length of 4, over the hypotenuse, which is 5. And now we're going to look at tangent of the angle theta. So tangent theta is this time opposite goes first, so it goes on top. So the opposite length is 3 over the adjacent side to the angle theta, which is down here, 4. So just a quick review of how to use SOHCAHTOA using right triangles, and then another quick review of the Pythagorean theorem, which hopefully came back really familiar to you if you hadn't seen it in a while. Alright, in this next section I want to start by talking about the unit circle. But before I just show you a giant picture of the unit circle, I want to talk about where the idea comes from and what we're really looking for. So here I have this circle drawn, and I'm going to say that this circle in particular has a radius of length r. So here's my circle, it's got a radius of length r. Here's the center of the circle. And when we talk about the unit circle, we're literally asking for values on the circle itself. So I'm asking for these values here on the unit circle, right? Everywhere on the unit circle, I want to know those exact points. But to find those points, I'm going to need a way to sort of measure them. So behind this circle, I'm going to go ahead and put an xy plane. So here is my xy plane that's behind the unit circle. So notice I'm putting the center of the circle at the origin at 0, 0. And then here's my radius coming from the origin and going out to the circle. So I was interested in finding this particular point on the circle, so it being an xy point. So in order to find those two values for x and y, what I'm going to do is I'm going to use right triangles. So the right triangle that I'm going to create includes the radius as part of it. So the radius is part of the right triangle. And then once I get to the point that I'm searching for on the unit circle, I'm going to drop down a vertical line straight to the x-axis, because that's going to create my right triangle for me. So here I have a right triangle, and then over here in the corner I have an angle. I'm going to call it theta. That now corresponds to this particular radius and this point xy. So now sort of the key is that this length here, this length right here along the bottom, is of length x. So if this coordinate point is x, how would I get to this coordinate point? Well, I would move to the right, x units, and then I would move up, so that means this vertical length here is considered to be y. So notice that I have this triangle with an angle, and I have its opposite side, its adjacent side, and its hypotenuse. So that's where the trig functions come into play. So if I want to find x and y, I'm thinking about using either sine, cosine, or tangent. So now what I did was I took out that little triangle that was inside of the circle, and I just want to analyze that for a second. So if here's that angle theta, and I want to consider sine of that angle theta, well, sine is going to be the opposite side, which we said was y, over the hypotenuse, which we labeled the radius r. So sine of theta is now y over r. If we're talking about cosine of the angle theta, well, now cosine is x over r, so the adjacent side of the hypotenuse. And then finally, tangent theta is opposite the y value over the adjacent side, the x value, so tangent is y over x. So if we wanted to find x and y, so let's go back to that. We're interested with the values on the unit circle. So we wanted to find x and we wanted to find y. As long as we have r and theta, we can find the x and y value. So here's what I mean by that. Let's go ahead and pull this to the side for a second. What if I have sine theta equals y over r, and what again was I looking for? I'm looking for y. So how do I solve for y? How do I get y by itself? I'm going to multiply both sides by r. So these r's will cancel out. So what does y equal? Y equals r times sine of theta. So if I want to find y, what do I need? I need to find an r, and I need to find that angle to substitute into the sine function, and then I have my value for y. So same thing with cosine. Cosine theta is x over r, so solving for x, I'm going to multiply both sides by r. So x is going to equal r cosine theta. So again, what do I need to find x? Just the same two values, r and theta. And then tangent, we don't really need tangent to find y and x. We just need sine and cosine to find y and x, or x and y, the coordinate point that we're looking for. So what we're going to do to make our life a little bit easier, actually, is we're only going to consider when we use special angles. And those special angles are going to be 0, 30, 45, 60, and 90. And we're also only going to consider when the radius of that circle is 1 unit, hence the unit circle. So when the radius here is 1, then this formula is going to be really nice. This formula is going to turn into just sine theta equals y over 1, which is really just y, right? So sine theta is going to equal the y value. So now let's take a look at the special right triangles. Alright, here are the special right triangles. So this comes from geometry and knowing the relationships when the angles are specific angles. So here, if I have a 30, 60, 90 right triangle, then the relationship between the two side lengths, if the hypotenuse is of length 1, is that opposite the side that's 60 degrees, I have radical 3 over 2, and then opposite the sides that's 30 degrees, I have 1/2. And then again, this is with a radius of 1. So you might be seeing this, used to seeing this with a radius of 2, which would mean that this side length on this side is going to be of length radical 3, and then this side length is going to be 1. But again, we're dealing with the unit circle, so that's why I just went ahead and divided everything by 2. So if you're used to the one with 2, radical 3, and 1, that's fine, as long as you know you divide everything by 2. And then the other special right triangle has angles that measure 45 and 45, so that the other angle, of course, is a right angle at 90 degrees. And then opposite each of those side lengths is radical 2 as the length, because the hypotenuse is, of course, 1 again. So I want that hypotenuse, or that radius, to be 1 in a 45, 45, 90. So finally, just making sure that we really understand the unit circle to recap. So here we only have just the first quadrant of the unit circle. So here I have this radius, and it's of length 1. So I'm interested in, again, finding this coordinate point on the unit circle. So to do that, what I have to know is I have to know this length here, this x length. So x is going to be equal to cosine of theta, and then y is going to be equal to sine of theta, and that's going to allow me to find this coordinate point x, y. And that is, again, because we are going to know the angle measurement here. So just as a quick example, we're going to use those special right triangles that we took a look at in the previous section. So let's say this is a right triangle, and it is a 45, 45, 90 right triangle. So if each of these is 45, then I want to find each of these side lengths. So that would mean this side length here would have to be radical 2 over 2, and this length down here would also have to be radical 2 over 2 if this radius is 1. So that would make this coordinate point, well, this distance, right, how do we normally get to a coordinate point? We either move right or left or up or down, so I have to move right, radical 2 over 2. So this point is radical 2 over 2, and I have to move up a length of radical 2 over 2. So that's what this coordinate point is, radical 2 over 2, radical 2 over 2. That's the x value and the y value. So those are the types of answers that we're going to be getting on the unit circle. So we're used to plotting points that are a little bit nicer, right? Because that's kind of what we're thinking about is, if we plot the point 3, 2, well, that's really easy, right? So I go over 3 and up 2. But radical 2 over 2 is just a number. It's about 1.4. So we're really just plotting points here. We're trying to find the coordinate points on the unit circle. They're just not as nice of numbers as we're thinking about, or we're used to thinking about. Alright, so here we have it, the complete unit circle that you are responsible for memorizing. Now, I do have a way that I teach to not necessarily memorize the entire unit circle, but how to find any value on the unit circle, and I will be teaching that method in this video. But if you know a different way and you're completely comfortable using your alternate method for evaluating any angle on the unit circle and you get the right answer, then I am fine with that. Then you don't need to learn my method, but I really want you to give it a chance and watch this portion of the video. So here's the entire unit circle. As I mentioned earlier, in calculus we deal with radians. So this here gives us all of the angle measures on the unit circle in both degrees, so from 0 to 360 degrees, and in radians from 0 all the way around to 2 pi. So we're interested in this portion here, right? Skipping that 90 and this 270 I'm about to highlight. We're interested in the radian measures only. So if you were looking at the unit circle, I want to make sure that you understand what exactly we're searching for when we say we want sine of some angle measure. So let's say I want sine of pi over 3. So looking at the unit circle, I would expect that you know that sine corresponds to the y value, as we talked about earlier. So sine corresponds to the y coordinate. So here, if I'm looking at the unit circle, I would go to pi over 3. So here's pi over 3. I would look at the coordinate point, and I would say, well, I'm interested in sine, so I want the y value. So my answer to sine of pi over 3 is radical 3 over 2. Here's definitely what it's not, and a lot of students do this, and it's definitely incorrect. So some students will want to convert pi over 3 into degrees and say that that is the answer to this problem. So they'll say, well, sine of pi over 3 equals 60 degrees, right? Absolutely not. That does not make any sense. So what is the right answer, or an alternate way to write this particular answer, is to say that sine of 60 degrees is also radical 3 over 2, because you substitute in, remember, what goes in here, what goes plugged in for the angle, it has to be in radians or it has to be in degrees. But your answer has to come out a number. So it can't come out in degrees. That doesn't make any sense. So it has to be the x or the y coordinate from the unit circle that comes out of the problem. Let's just try a couple more real quick. Let's say I want cosine of 4 pi over 3. So the cosine function now corresponds to the x value. Sine corresponds to y, cosine corresponds to x. So cosine of 4 pi over 3, so we find 4 pi over 3 on the unit circle, and we look at the corresponding coordinate point, and cosine is going to be the x value. So the x value is negative 1/2. So cosine of 4 pi over 3 is negative 1/2. And let's go ahead and try another one. Let's say we want sine of 2 pi over 3. So we find 2 pi over 3 on the unit circle. Sine is the y value. So we have radical 3 over 2. So notice sine of pi over 3 was radical 3 over 2. And sine of 2 pi over 3 is radical 3 over 2. So just to actually do one more, let's do sine of 4 pi over 3. So let's find 4 pi over 3, which we already had from cosine. Sine of 4 pi over 3 was down here. Now we want the y value, which is negative radical 3 over 2. So let's look at that for a second. Sine of pi over 3, that was radical 3 over 2. Sine of 2 pi over 3, that was radical 3 over 2. And sine of 4 pi over 3 was negative radical 3 over 2. So I want you to just look at that pattern for a second. So we had pi over 3, 2 pi over 3, and 4 pi over 3. What do they have in common? Is that pi over 3 in each of them. And the answer was either positive or negative radical 3 over 2. So we're going to actually use that coming up in just a few minutes on trying to evaluate them without actually looking at this unit circle. Alright, so before I go ahead and show my method for evaluating any trig function on the unit circle, what it is based on, what it is founded upon, is on this chart. And you'll see a lot of the students who took me for honors math analysis create this chart on their paper over and over again. And I'm absolutely fine with that because it is really easy to recreate. So just to show how this works, and then I'll show you how to recreate it, what this is saying is that, well, here are the angles in degrees or radians that we're substituting in. So these are the ones that we're responsible for, at least in quadrant 1. So 0, pi over 6, pi over 4, pi over 3, and pi over 2. So those are in the ones in radians. Those are the ones we really want to make sure we know this year. And let's say we want sine of pi over 4. So what we do is we go to the sine column. So sine of pi over 4 corresponds to radical 2 over 2. And if I want, let's say, cosine of pi over 2. So now cosine of pi over 2 corresponds to 0. So that's how the chart works, but, where do you get the chart from? How do you recreate it? So here's what you definitely have to know. So I'll just go ahead and recreate it down here on the bottom, kind of small. You have to know the angles and the order that they appear in. So the angles are 0, pi over 6, pi over 4, pi over 3, and pi over 2. So there are 5 angles that you need to know. And then what comes first is sine, then cosine, and then even tangent. And so here's the little trick to creating this chart. So what you do is you start down this first column, the sine column, and you write the numbers 0, 1, 2, 3, and 4. And then the next step is that you square root all of those numbers. So the square root of 0, the square root of 1, the square root of 2, the square root of 3, and the square root of 4. And then you want to simplify those. So 0, square root of 0 is 0, square root of 1 is 1. Square root of 2, well, that's the same. Square root of 3, can't simplify that. The square root of 4, well, that's 2. And then what you do is you take those numbers and you divide them all by 2. So I've divided everything by 2, and then you're going to simplify one last time. So 0 over 2, that's 0. 1/2 stays 1/2. Radical 2 over 2 stays radical 2 over 2. Radical 3 over 2 stays the same. But 2 divided by 2, well, that's 1. So notice those are the same values that you see here. 1, 1/2, rad 2 over 2, rad 3 over 2, and 1. Now that may have seemed like a little bit of work, but the nice thing is that to find the other 2 columns, we don't have to do quite as much work. So to find cosine, what we do is we flip all of the values from the sine column. So 1 was the very last entry in the sine column. It becomes the first entry in the cosine column. And then radical 3 over 2, that was second to the last, so that becomes the second one in cosine. Rad 2 over 2 stays in the middle, then 1/2, and then finally 0 is going to line up down here. So you just flip all of the values. And then tangent, well, it's important to remember tangent is y over x. So remember, sine corresponds to y, cosine corresponds to x. Tangent is y over x, which is like saying sine over cosine. So here, sine is 0, cosine is 1. So what's 0 over 1? 0. And then here, 1/2 divided by radical 3 over 2. Well, that simplifies to rad 3 over 3. And then radical 2 over 2 divided by radical 2 over 2, so sine over cosine. The same number over the same number, that's 1. Rad 3 over 2 divided by 1/2, that's going to simplify to rad 3. And then finally, we have 1 divided by 0, and 1 divided by 0, right? 0 on the bottom's bad, so that is undefined. So that's how I recreate the chart. So we start out with the 0, 1, 2, 3, 4, square root everything, and then divide everything by 2. And then you flip your column to get cosine, and then you remember that tangent is sine divided by cosine. So you take each of those entries and divide them to get the chart. But then once you get the chart, this is going to allow you to use reference angles to find any other angle on the unit circle pretty quickly. Alright, let's go back to the unit circle for a minute and talk about two quick things, the quadrants and reference angles. So here I did mention earlier, but I will formally say the quadrants that these are labeled are quadrants 1, quadrant 2, quadrant 3, and quadrant 4. So they do go in a counterclockwise direction, starting at the top right and going around. And then something else that we need to know about the quadrants is a little phrase to help you remember which trig functions are positive in those quadrants. So the phrase is, all students take calculus. And for you guys, that's true, right? All students take calculus. And what this means is that in those quadrants, that's the function or functions that are positive. So in quadrant 1, A stands for all. So all trig functions are positive, all meaning sine, cosine, tangent. In quadrant 2, only the sine function is positive. So S stands for sine, so sine is positive. In quadrant 3, only tangent is positive, and in quadrant 4, only cosine is positive. So that's the first thing we needed to just review. And the second thing is reference angles. So reference angles is actually a really nice concept when we're talking about radians. So the formal definition of a reference angle is the angle that's the shortest distance away from the x-axis. So let's just highlight the x-axis here for a second. Can't draw a straight line too well. Let's say we are looking at 2 pi over 3. So the actual angle here would be from the positive x-axis all the way to 2 pi over 3. So this is the main angle. And a reference angle is how can I quickly get to the x-axis, so that blue line that I drew. So the quickest way to get to the x-axis is to go how far? Well, in radians, this is actually just going to be pi over 3. And I don't have to do a lot of work to think about that, and here's why. To find reference angles in radians, all we need to do is remove the constant in front of the pi in the numerator. So the reference angle to 2 pi over 3, so the reference angle, I'm just going to abbreviate it like that, is pi over 3. So let's say, what about 4 pi over 3? So the reference angle to 4 pi over 3, I just remove the number in front of the pi, so it's also pi over 3. So let's think about that for a second. The main angle would be from the positive x-axis, and I'd have to go all the way around to 4 pi over 3 down here. But what's the quickest way for me to get back to the positive x-axis? So this would not be the quickest way, right? That's further than going this amount here, but that amount is pi over 3. And the easiest way to think about it is just taking off that front number in front of the pi. So reference angles are going to be important because I'm actually going to highlight all of the angles with reference angles pi over 3. So 5 pi over 3, and then also up here at pi over 3. So we did this earlier a bit, but we're just going to do it again right now to see that pattern clearly. So let's say let's do cosine. Let's say I want cosine of pi over 3. Let's say I want cosine of 2 pi over 3, cosine of 4 pi over 3, and cosine of 5 pi over 3. Alright, so cosine of pi over 3, and again, we're assuming we're not looking at this chart, right? That this is not here. Cosine of pi over 3 is a value that you need to know because it's in quadrant 1. And how do you know this value? Well, you memorize the table. So there's no getting out of that. You have to at least know the table. So cosine of pi over 3 from the table, we should know, is 1/2. So looking at the unit circle, because it's here, we know cosine is the x value at pi over 3, so it's 1/2. Alright, we would know that. But cosine of 2 pi over 3, well, that's not in the chart. But here's what I do know. Cosine of 2 pi over 3 is the same as cosine of the reference angle. What's the reference angle? We just remove the 2. So cosine of 2 pi over 3 equals cosine of pi over 3, but the answer might be negative. So cosine of 2 pi over 3 is either positive or negative cosine of pi over 3. So our answer is either going to be positive or negative 1/2. But how do we decide if the answer is positive or negative? Well, we have to know where 2 pi over 3 is, in which quadrant in the unit circle, and then we have to remember all students take calculus. So 2 pi over 3. So another thing that we're going to have to remember is that this is 0, this is 1/2 pi, this is 1 pi, this is 3 pi over 2, which is like 3 over 2 pi or 1/2 pi, and then 0 is also 2 pi again. So if I want to think about where is 2/3 pi, right? 2 pi over 3 is 2/3 pi. 2/3 is between 1/2 and 1. So that would mean that this angle falls in quadrant 2. And again, we're not going to be staring at the unit circle because, of course, you could just stare at it right now and say, well, 2 pi over 3 is, of course, in quadrant 2. But we would have to figure that out. So 2 pi over 3 is in quadrant 2 because 2/3, the original angle, is between 1/2 and 1. So in quadrant 2, which is the only trig function that's positive? Sine is the only trig function positive. So that means that it's not plus or minus, it's just minus. So what was cosine of pi over 3? It was 1/2, so the answer is negative 1/2, which we can see because we're looking at the unit circle. So now cosine of 4 pi over 3 is going to be, well, that's going to be the same as the previous one. It's either going to be plus or minus cosine of pi over 3. But which one is it? Is it plus or minus? So the reference angle is still pi over 3 because we just kind of cross out the 4. And plus or minus depends on the quadrant. So 4 pi over 3. And sometimes students have a hard time with this. Sometimes this is easy for them. So if this is easy for you, then just, move on. But if you don't know where 4 pi over 3 is, so let's think about it as a mixed fraction. 4 over 3 is like 1 1/3. So if this is 1 and this is 1/2, then 1 1/3 would have to be down here in quadrant 3. So if I'm in quadrant 3, only tangent is positive, so that means cosine has to be negative. So my answer is again negative 1/2. So you're noticing that pattern, right? When they all have the same reference angle, they're all going to be some version of 1/2, positive or negative. So now cosine of 5 pi over 3, so it's either going to be positive or negative cosine of pi over 3. We have to decide, is it positive or negative? Well, 5 pi over 3, using that same mixed fraction logic, 5 pi over 3 is 1 2/3. So if this is 1/2 and this is 2, then 1 2/3 is between 1/2 and 2. So I'm in quadrant 4, which cosine was the only one positive. So now we can erase the negative, and our answer is, again, positive 1/2. So that's sort of my way of evaluating functions on the unit circle. So let's go ahead and do some more examples without looking at the unit circle. Alright, so here we go. We're going to answer these questions using reference angles and radians to evaluate trig functions. So here are the functions that I'm going to try to evaluate, and let's assume that you've written out this chart on your paper. So I just left this chart up here that we recreated earlier. So let's go ahead and say you scribbled this down and now you want to evaluate these trig functions. So sine of pi over 3. So if you've done it correctly, sine of pi over 3 is radical 3 over 2. Sine of 5 pi over 6. So here's what you know, that sine of 5 pi over 6 is the same as sine of pi over 6, whatever that is, and then it's either positive or negative. So it's not both. I want to make sure you don't leave your answer like this, plus or minus. It can't be both. It has to be one or the other, positive or negative. So it's like, which one, positive or negative? So how do we decide that? Where is 5 pi over 6? So we're thinking about our own little unit circle. Here's 0, here's 1/2 pi, here's 1 pi, here's 1.5 pi, and then 2 pi. So we also have to remember all students take calculus. So where is the original angle, 5 pi over 6? So 5/6 as a fraction is pretty close to 1, so it's over here in quadrant 2. So that's where sine is positive. So we know that our answer is going to be positive sine of pi over 6. So here on our chart, sine of pi over 6 is 1/2. So our answer is positive 1/2. And what's sine of pi over 2? So sine of pi over 2 is one of those special angles that you need to know. So pi over 2 is 1/2 pi. That's this vertical angle at the top here. So on the unit circle, this coordinate point is 0, 1. So if I want sine of pi over 2, that's the y value, that's 1. It is in the chart for you, sine of pi over 2 is 1, but it's important to know the angles 0, pi over 2, pi, and 3 pi over 2, also known as the quadrantal angles. Now let's do some cosine functions. So cosine of pi over 4, just looking at the chart, cosine pi over 4 is radical 2 over 2. Cosine of 2 pi over 3. So some more practice with using reference angles. So cosine of 2 pi over 3 is going to be the same as cosine of pi over 3, but positive or negative, that's the question. So 2/3 pi. Where's 2/3 at? Well, 2/3 is between 1/2 and 1, so it's going to be in here somewhere, in quadrant 2, where only sine is positive. So this is going to have to be negative cosine pi over 3. So cosine pi over 3 is going to end up being negative 1/2, or cosine 2 pi over 3 is negative 1/2, because we got the negative because we're in quadrant 2 with the cosine function. And then cosine 3 pi over 2. So this is one of the problems that it doesn't work out to just think about the reference angle. This is a quadrantal angle. This is 3 pi over 2 is down here. Whoops, 3 pi over 2 is down here. So this coordinate point is 0, negative 1. So 0, negative 1, the cosine function is the x value. So cosine 3 pi over 2 is 0. So the quadrantal angles are special. 0, pi over 2, pi, 3 pi over 2, 2 pi. Those are ones that, again, you want to think about the coordinate points 0, 1, 1, 0, etc. But the trick using reference angles works when the reference angle is pi over 3, pi over 4, or pi over 6. And then tangent. So tangent of pi over 4. So tangent of pi over 4, that one's in the chart for us, so we could reference that as 1. And that comes up so much in calculus. That's just something you should know pretty quickly. Tangent of 5 pi over 3. So 5 pi over 3 is going to have a reference angle of pi over 3. So now it's deciding, well, 5 pi over 3, 5/3, what quadrant's that in? So 5/3 is 1 and 2/3. 1 and 2/3 is going to be way over here in quadrant 4, where the only function positive is cosine. So this is going to have to be negative tangent pi over 3. And looking at my chart, tangent pi over 3 is rad 3, so my answer is negative radical 3. And tangent 0 is just 0, right? Looking across at the chart, tangent 0 is 0. So there's plenty of problems on the second part of the summer assignment to help you review evaluating trig functions, and these are all to be done without a calculator, and your answers should be exact. And what I mean by that is I don't want to see cosine of pi over 4 is 1.414. No, that is an approximation. I need to see square root of 2 over 2, square root of 3 over 2, those exact answers, no approximated decimal answers. Trigonometric functions. So from the very beginning, I made sure to talk about how sine, cosine, and tangent are really functions. What you do is you take angles and you plug them into these functions, and what you get out are numbers. So what can we do with any function is we can graph them on an xy plane. So here we have sine, cosine, and tangent. So I've represented them using function notation. So f of x is sine x, cosine x, tangent x. And the sine and cosine functions look like these wave functions here. So they're doing what's called oscillating or oscillation, which means that they bounce up and down like waves. Now, I'm going to talk about the properties of these functions that you need to know. So you do need to know their basic shape. So let's start with sine and cosine. You need to know that they are oscillating in this wave-like pattern and that they oscillate between -1 and +1. So the very highest sine goes as 1, the very lowest sine can go as -1. And you should already know that because that is considered sine's range between -1 and 1. You need to know that the sine function starts at 0, 0. Well, it doesn't start at 0, 0, but that it does go through the origin because of course it does continue as a sine, as a waving oscillating function. And that it goes through pi, 2 pi, 3 pi. It goes through the multiples of pi. The cosine function, however, goes through the point 0, 1. So it's almost identical to the sine function. It's just shifted over a little bit. So the cosine function goes through pi over 2 and 3 pi over 2. So it's going through multiples of pi over 2. So 1/2 pi, 3/2 pi. It's going to go back over here and cross down at 5/2 pi. Those are the different x-intercepts of the cosine function. Tangent function is completely different. Here's what I want you to remember about the tangent function is that it looks like the cubic function. So it looks like x cubed, but it's infinitely many x cubed. So a lot of students draw me the tangent function and they only draw this middle part. But this is a periodic function. It keeps repeating over and over again. So what you need to know is that there are vertical asymptotes at the multiples of pi over 2, the odd multiples of pi over 2, and that it repeats. That's the most important thing. It looks like the cubic function, but it's a repeat of the cubic function over and over again. So it goes through 0, 0, but then it goes over here through pi 0. So there are all these infinitely many parts to the tangent function. It's not just the middle portion. And here's the very last thing I need you to know about trig is all of its special identities. So they all have names. The reciprocal identities I need you to know, so that the sine function is 1 over cosecant. So we didn't really talk a lot about cosecant, secant, and cotangent, and that's because you can rewrite cosecant as 1 over sine, you can rewrite secant as 1 over cosine, and cotangent as 1 over tangent. So cosecant, secant, and cotangent are so closely related to sine, cosine, and tangent that we don't really spend too much time talking about those in particular functions. It's also important to know the quotient identities. So tangent is sine over cosine. We did talk about that earlier. So cotangent is cosine over sine. The Pythagorean identities. So these are huge, especially this first one here. So sine squared plus cosine squared equals 1. And that does come from the Pythagorean theorem. And then tangent squared plus 1 equals secant squared theta, and 1 plus cotangent squared equals cosecant squared theta. I don't think these are necessarily worth memorizing because you can derive them. So let's say you know sine squared plus cosine squared theta equals 1. Well, if these two sides are equal, whatever I do to one side I can do to the other side. So let's go ahead and divide everything by cosine theta. So whatever I'm doing to one side, I'm going to do to the other. So let's divide both sides by cosine squared. So sine squared over cosine squared. So what's sine over cosine? It's right here for me. It's tangent. So tangent squared plus cosine squared over cosine squared, same thing over the same thing, equals 1. 1 over cosine squared. So what's 1 over cosine? It's secant. So this is secant squared theta. So what happened? I just found the second identity. So if you've memorized the first identity and you know your reciprocal and quotient identities, you can just derive these other two formulas. So you get this second formula if you divide everything by sine instead of dividing everything by cosine. So that's a nice little trick. And then odd and even identities. So I'm not necessarily sure, again, this is like worth memorizing the way it's written. It's just important to know that sine is an odd function, What does it mean to be odd? I can rotate it around the origin and it lands right back on top of itself. Cosine is an even function, so I can fold it over the y-axis and it's the same function. And tangent is an odd function, so again that rotation around the origin gives me the same thing. So that's kind of what these even-odd identities are saying, is that property that they have graphically. That's important to know. So that's it for this review about trigonometry. Again, it is a review, so if you feel like you need more practice, I encourage you to go online and find additional videos that cover these particular topics involving trigonometry. It doesn't matter how you know the unit circle, but you need to know the unit circle and all of these properties that are here. I encourage you to make note cards, printouts, whatever you need to make sure that these topics are known before you come to class, because it's going to be so easy to fall behind if all of this just seems so far away from you and that you knew it at one point but you don't remember. It's time to make sure that you really have mastered all of these concepts before coming to class.